Saturday Morning Physics is sponsored by the M. Lois Tiffany Endowment, the Hideko Tomazawa Endowment, the Physics Department, and by gifts from friends of the program.
In the title of my presentation, I have the word hydrokinetic energy. Hydrokinetic is the energy that we have in water flows. And it comes in two forms. Horizontal, which is what I am working on, which we have in currents, rivers, tides, and so on. And then vertical, which is the energy that we have in waves. The device that we have invented at the University of Michigan and we have patented through the University of Michigan harnesses horizontal hydrokinetic energy. And we do that by enhancing flow instabilities. And I will be talking about those today. Actually, one form, the most common form of a flow instability is a fluid-structure interaction phenomenon. And it's called vortex-induced vibrations. So VIV here in the name Vivace stands for vortex-induced vibrations. And the rest is aquatic clean energy. So we use the term vivace, which you know very well what it means in music. Of course, I'm not the only contributor. This is a big project. It's like inventing a new machine and trying to make a product out of it. And it has lots of scales of applicability. So we're handling the hydrodynamics at the Marine Renewable Energy Lab. It is part of the Marine Hydrodynamics Lab, which is around the corner. And also, back in 2005, I started a company called Vortex Hydro Energy. Now I'm the Chief Technology Officer of that company, and I have other people running the company. So Gus Simio and Rebecca Macklem are the two chief people in Vortex Hydro Energy. The power takeoff system, we work it with students in electrical engineering with a lot of help from the Ocean Energy and Engineering Systems Lab at Virginia Tech. And the environmental aspects of this work we study with Oak Ridge National Lab. It's a big project, and the more people get involved, the faster it's going to be a product. I have a quick overview so that you know what where we are today. And then I have three parts, some background information. It's a little bit technical. I'll do my best to explain things so that everybody can understand it. And then it's the development part of Vivace. And finally, some research advances that we made in the lab in order to be able to make this product a reality. So in the background, I'll talk about marine renewable energy, flow-induced motions, and marine hydrokinetic energy converters. Then about the stages of development. There are 5 stages for developing a product to put it in the ocean. We've gone through the first 3. And then I'll talk about some research advances that we made. Okay, so a quick overview. The problem that we face is low-cost energy sustainability. And of course, you know how challenging the problem is. We cannot solve it by using only one source of energy or one piece of machinery. We have really to use everything that's available with the objective, of course, in about 30 to 50 years to have a sustainable power supply. And by sustainable, we have, in sustainability, we have 2 components. One is that the source of energy is clean and renewable, and the other that the technology we use is environmentally compatible. For example, hydropower is clean and renewable, but the footprint of dams, for example, is very big. The challenge that we face when we harness hydrokinetic energy is that currents are typically slower than 3 knots, and rivers are typically slower than 2 knots. But turbines, they need an average of 5 to 7 knots to be financially viable. Of course, there are exceptions, like the British Channel current goes up to 15 knots. Southwest of Korea, the current is up to 12 knots. The East River in New York which is not a river, actually. It has speeds going up to 8 knots. And there is a total of 7 sites in the United States where velocities are in the range of 5 to 7 knots and higher. So with this technology, I believe that we are opening up accessibility to a vast amount of energy, which right now is not accessible. And there are lots of applications of this technology that we will talk about. Funding is coming from, for basic research that we do in my lab, comes from the Office of Naval Research, the National Science Foundation, the Department of Energy, and for the prototype development, it's coming from the Naval Facility in Port Hueneme in California, and the Michigan University Commercialization Initiative and other sources. Yeah. This is where we are today. On the right, you have an underwater camera, and you're looking into the current, so the flow is coming out of the board, if you will, out of the screen towards us. And the steady flow in the St. Clair River is driving the 2 cylinders transversely. And on the left, you have, it's the test section, part of the test section of the channel we have in the Marine Renewable Energy Lab. What you see is the cylinders are horizontal. The cylinders are horizontal, supported by struts and suspended by springs. So each one of these cylinders, or Vivace converter, is a very simple machine, just a cylinder transversely to a flow, and the flow, the steady flow, drives the cylinders transversely. So it behaves like a 4-cylinder reciprocating engine where the fluid, where the fluid flow is the fuel, but at the same time, it's camshaft and all the connectors, mechanical connectors. There's no mechanical connector there. Everything is hydrodynamically connected. Right, so let me start by giving a quick background. There have been many studies, as you probably know, of the challenges that the world faces, and energy always tops the list. Water comes second. But if we can actually solve the first problem, then we can do something about the second one. The issue, of course, is that we need a lot of energy in order to desalinate water. So I would say that the problem we face, the top problem, the top challenge that we face, is sustainable generation and storage of clean and renewable energy at a competitive cost. How much renewable energy do we have? Well, to put into perspective, this is how much we are typically consuming in a year, about less than half a zettajoule. Joule is a very small number, but zetta is 10 to the 21. And you can see biomass captures about 5 times as much, 4 times as much. Winds can supply about 12 times as much, and oceans absorb about 600 times as much energy. So the marine energy is about 97% of the energy that we get from the sun, after, of course, reflection radiation from the atmosphere and the surface of the Earth. But where is that? Unfortunately, most of it is in ocean thermal energy, and there are devices that can harness the ocean thermal energy, but they are big and expensive and not particularly scalable. On the other hand, we have plenty of energy in waves and also in tidal and in salinity gradient. And you can compare this to the world electricity consumption, which is about 17,000 terawatt. The Electrical Power Research Institute in California has done several studies, and these numbers basically represent what we can harness with present technology. So hopefully, with new technology coming up every year, we will be able to access more of that energy. Marine hydrokinetic energy converters. I have 2 categories here. The top one are 3 of the 5 concepts that harness energy from waves. So they harness the vertical hydrokinetic energy. The one on the left is Australian, the buoy is American, and this one is British. The buoy is a point absorber. It floats on the free surface, and then with a mechanism, you convert this hydrokinetic energy to mechanical, and then mechanical to electrical. But it's a point absorber, one point on the surface. This design is like a long snake. It's about 400 feet long, about 13 feet in diameter. It has 4 rigid components and 3 joints that have hydraulic valves in it, and this way they harness the energy. And this one is a surface absorber. It's the so-called oscillating water column. Water comes in, or waves come into this chamber. They push the air up, and the air goes through another chamber that accelerates it and goes through a turbine and generates electricity. So this is a surface absorber. And these are underwater devices. They're all turbines, as you can see. This is the Verdun turbines. I'm sure you've heard of those. They're about 5 meters in diameter. This is American. This is British. Each one of those monopoles has 2 propellers. Each one is 12 meters in diameter. They're pretty big, so we're talking about 40 feet in diameter propellers. This has not been built yet. It's 20 meters in diameter, 20.5 meters long. And typically, they're designed for velocities 5 knots and higher. And if you use in the ocean a turbine like this one, the lunar energy turbine, then you need to leave behind it a space of about 235 meters because they create a wake with a lot of turbulence. And that's what brings the power density down, which we're going to talk about in a few minutes. And basically, power density is the Achilles heel of all renewable energy technology. In other words, you need a lot of space, a lot of volume, in order to be able to harness a relatively small amount of energy. And that's where, of course, fossil fuels are much more advanced than we are. Let's talk a little bit about flow-induced motions. If you have a body in a fluid, the body, if it's rigid, usually just measure the forces in engineering and we can easily design. But if it's flexible, either because it's like a car antenna, a building, a pipeline, a cable, anything which is flexible, gets into vibrations. And that's the difficult part. Now, the presence of the body, of course, changes the fluid. The fluid generates vorticity that drives the body. So there's a fluid structure interaction phenomenon. There's a coupling between the fluid motion and the body motion. And that generates some instabilities. One of those is vortex-induced vibrations that we'll talk more about. There's an even more vigorous motion, which is called galloping, and there are several forms of galloping. And then there's an even more vigorous motion, buffeting, and bluff bodies, that is not slender bodies, bluff fat bodies, get into VIV, galloping, and buffeting. There's another form of instability, like flutter instability. This is what airplane wings do. Okay? So in this technology, we started with VIV, but we're using both VIV and galloping now. I don't think that we can use buffeting because buffeting is affected by ambient vorticity, which is a random event, and you don't want to design a machine based on randomness. Okay. So let's look at VIV first. What I have in this little picture from a lab, this is about a foot by a foot. This is a cylinder in a steady flow. And even though you have a circular cylinder, even though you have a symmetric body in a symmetric flow, the wake is not symmetric. So what happens, vortices get generated. And the only stable pattern in nature actually is that of perfectly alternating vortices. So that introduces a periodicity into the flow. So when you have a periodic excitation, then if the system has a natural frequency, it will respond to that. And then you get into resonance, which means a lot of energy going from the excitation to the body, which, of course, is what we're trying to avoid in engineering. I'll come back to the previous picture. I want to show you a more realistic picture at higher velocities and higher at higher velocities and higher diameters. Let me make a parenthesis here. Most of you probably know Reynolds number, but what it is, think about it as velocity times diameter. So the bigger the cylinder, the bigger the Reynolds number, the bigger the velocity, the bigger the Reynolds number. Okay? And you can see how this is a cylinder. We have a boundary layer. That's a very thin layer of fluid in contact with the body. That's where all the vorticity gets generated. And when you have a bluff body like this, vorticity goes through this interface between the laminar flow, the external flow, and the turbulent flow here, and rolls up. If you have an airfoil, all this vorticity just goes into a narrow wake and goes away. But if you have a bluff body, for reasons that are not quite well known, it rolls up, and it forms large vortices. So in this pretty turbulent flow, there is structure. And that structure is very periodic. And now we talked about the resonance and what happens. So I want to explain now the difference between VIV and a regular resonance phenomenon. This is like a little oscillator. Okay? It has its own natural frequency. I just pushed it out of the way, and this is the preferred natural frequency. Okay? Eventually, the motion will die out unless I keep moving it. Okay? Now, if there is an excitation that synchronizes with the motion of the body, with the preferred frequency of the body, then a lot of energy from the excitation goes into the body, and the amplitude keeps increasing. Okay? That's resonance. That's what we try to avoid in engineering. When you have a flexible structure, you want to make sure the natural frequencies of the system are not anywhere near excitation frequencies. So, for example, if you take this one, which has its own preferred natural frequency, but you excite it with very high frequency motion, it doesn't go anywhere. Okay? And if you excite it with very slow amplitude, it just follows the excitation. Okay? That's a linear oscillator. The good thing about a linear oscillator, from the engineering point of view, is that it has a very narrow bandwidth. In other words, once you get a little farther away from the natural frequency, the response is low. Vortex-induced vibrations is exactly the opposite. There is the so-called lock-in phenomenon. The motion of the body grabs the vortex excitation. So what happens, the vortices, instead of shedding at their own frequency that they would shed if you had a stationary cylinder, they lock onto the motion of the body, and they shed when the vortex, when the body moves. So what you have here in the pictures, in the two animations, is the cylinder goes to one end and sheds a vortex. It goes to the other end and sheds a vortex. That's like synchronization. You synchronize the excitation that you get from the vortices with the motion of the body. So that's like linear resonance. The big difference is that this lock-on phenomenon occurs over a very broad range of synchronization. This grabbing of the excitation happens over a very long range of excitation. Let me try to explain this. If my hand was not that strong compared to the mouse here, to this oscillator, then the oscillator, if you could think, would grab my arm and push it at the frequency it wants, regardless of what the external velocity is. Okay? So in practical terms, if we design something like this to operate at 3 knots, it will work equally well between 2 knots and 4 knots. Okay? So imagine what a catastrophe this is in engineering, where instead of trying to design to stay away from one frequency, you're talking about a very broad range. And in practice, this is about natural frequency plus or minus 50 to 60%. So that's why I mentioned 2 to 4 knots. So let me show you this graph and explain what I said a little bit better. I have here 4 oscillators. The first one is a linear oscillator. As I said, it has a very high peak at the natural frequency. And once you get a little bit far away from the natural frequency, the amplitude drops significantly. Then this is a vortex-induced oscillator, but at low Reynolds numbers. What happened when we first started this work, we looked at the thousands and thousands of publications that we have on VIV, and there was very little information on bigger bodies and high damping. We need damping in order to harness the energy. Without damping, you can't harness energy. You can't walk on ice. You need some friction to be able to walk. That's exactly the same concept. And so the oscillators at low speeds and small bodies exhibit like an upper branch and then a lower branch and then desynchronization. So you can see here, in terms of this dimensionless velocity, this runs between about 5 and 10. So you double the velocity and you still have a system in synchronization. Consider that a resonance. When we started doing our experiments, there was nothing in that domain of bigger bodies, bigger Reynolds numbers, velocities, and so on, and nothing in high damping. Everybody was trying to work with low damping so to see how the response of the system is. But then we have a very different behavior when we go to high velocities and high damping oscillators. If you take this and you superpose it on this one, it goes up to 1, and then down to 0.6, and then desynchronizes. In our case, routinely, even with a smooth cylinder, we got up to about 1.9 diameters amplitude. So we're talking about total stroke of 3.8 diameters. You can imagine if you have an offshore platform or pipeline, which is of circular shape, if it moves like 2 diameters to one side and 2 to the other, it's not going to last very long. So that was the first thing that we did. We made it work over a broad range of synchronization and considerable amplitude. And then the next one, we started introducing turbulence stimulation. That mimics fish scales. We're learning quite a bit from fish kinematics. And let me explain a little bit more about galloping. Galloping is much more severe than VIV, and I'll show it to you in a video in a few minutes. And galloping doesn't have an end. Once galloping starts, we never know where it ends, like until the structure collapses. So for example, wires that transfer electricity, they come in a group of 5 or 6. And if the wind blows transversely, the ones in the back get into galloping because of phenomena caused by the leading wires. These will keep moving until there is collapse. We don't know experimentally where that ends. But that starts at this parameter that I talked about earlier, the velocity, non-dimensionalized velocity or reduced velocity. Starts at about 20. And VIV ends at about 10. With the turbulence stimulation that we introduced, which again mimics fish scales, we brought galloping down to about 11 and VIV up to about 11. So now we have oscillators that have back-to-back VIV and galloping. They're both flow-induced instabilities. So as soon as we start this high amplitude response, there is no end to it. Here it appears that it ends, but this is just limitations of my lab. Here with more damping, you can see it keeps going. So these are the 4 types of oscillators that we have. The first one is linear. The other are nonlinear. And this is what we are doing with Vivace. So that was a background introduction. Let me talk a little bit about the development of Vivace. And this is very rewarding, actually, because I had lots of help from the Office of Technology Transfer to be able to start a company. I had absolutely no idea how to start a company and how to make it grow and then have other people do it. And the machine is so simple. It's just each one of those is just a cylinder suspended by springs. It's that simple. So it may take like a year and a half sometimes to get a new development in the lab, but it takes a few minutes, literally, to get it from the lab to the product. So that's a very rewarding experience for a university professor. It's something new. And there are 5 stages of development. There's no way that actually you can take one concept and put it in the ocean and make it work. You have to go through several stages of development at increasing scales. Particularly in the ocean environment, computers cannot help us no matter how fast they are. It's going to be at least 20 more years before we have a numerical towing tank. The towing tank is around the corner in West Hall. Okay. And this is one form of flow-induced instability that I'm sure you have all seen. Right? Back in 1940, when the Tacoma Narrows Bridge collapsed, von Karman said that this is vortex-induced vibrations. In the past 2 or 3 years, there has been some discussion whether this is flat Earth instability, it's Hopf bifurcation, various other forms. But either way, VIV is a very important part of this. And on the right, you have a maybe not so well-known disaster. In 1965, in Fairbridge, England, these cooling towers were constructed, but when they were designed as standalone towers. You can see how big they are. These are buildings down here. Okay? And one day, the wind blew from right to left, from right to left, and these 3 towers were found in the wake of these 4 towers, and in a matter of minutes, they collapsed. That's how much power there is in those flow-induced instabilities. Okay? We already talked about this cartoon down here. What I want to say is that the objective of what we're doing is to capture the abundant hydrokinetic energy in even low-speed ocean and river currents without using dams or turbines. The approach that we use, if it's vortex-induced vibrations, we enhance vortex shedding, we maximize VIV, and then we harness the energy instead of trying to mitigate it. And with galloping, similar way, we enhance a different form of instability that I will explain, and we harness the energy. There are 3 important factors from fish biomimetics that have given us guide. First of all is the surface roughness, the scales. They have a tremendous impact on what we're doing. The second one is the proximity of cylinders, as you will see when I show you again the video with multiple cylinders. If you can imagine a school of fish in an aquarium, you see that when they speed up, they tend to gravitate at certain distances between them. Well, what happens is the following. First of all, if you take a fish model and you tow it in the towing tank to find the resistance, the drag, is much higher than their muscle power. So how do they move? They curve their bodies, they collect a large vortex, they straighten their bodies, shed that vortex, collect one on the other side, and they keep gliding between the vortices. When you have a school of fish in an aquarium, you see how they wiggle. They basically glide between vortices generated by fish ahead of them. Okay? And that's the way they can move fast really in water. And this is also a very interesting concept because at the beginning when I presented this idea, the Office of Technology Transfer was getting feedback from investors and other people that this is kind of strange, exotic. But we live in air, and what we observe is lifting surfaces. Bird wings, airplane wings, windmills, sails of sailboats, they are all lifting surfaces. In a steady flow, they generate a steady lift. But in water, things do not move that way. In water, all the lifting surfaces that we have, like fins of fish, they are for navigation, not for propulsion. They do the propulsion with the mechanism that I described. Anything that moves in a dense fluid, from tiny sperm to huge whales, they are a bluff body with a tail. And that's the way they can move fast in a fluid. So in the ocean environment, in the water environment, this is the natural way of moving, not lifting surfaces and blades. So back about 5 years ago, this is the first machine that we put together. What you see is the test section of the channel, the recirculating channel. It's a pretty big facility. It's 2 stories high, and it recirculates 8,000 gallons of water. And the flow is from left to right at a speed of 0.8 meters per second. And it's this flow that drives the cylinder transversely. No, nothing else drives the cylinder. And all it is just this cylinder suspended by those springs, sliding on shafts. And then we have a very simple mechanism of transmitting the motion to a generator which lights the bulbs. So that was the first realization of the concept. And this is my favorite picture. You've already seen this one. This is about a foot by a foot. Reynolds number 100. Very, very low number, very low speeds, very low diameter of body. This is about 5 miles by 5 miles. It's a NASA picture. This is the peak of a mountain piercing through clouds. And you can see the periodicity in the wake. You have a very turbulent flow, and you can see the structure within that turbulent flow. So you have a periodicity. And what happens, I'll try to make this simple. What happens is you have everywhere this street of vortices, which is called the von Karman vortex street, except for transition here. Let me explain what this is. This is either for a sphere or for a cylinder. This is like the Reynolds number. Think about it proportional to velocity. And this is the drag coefficient. Golf balls operate right here. Why? You go through laminar flow. Nobody's strong enough to hit the golf ball to go any faster. So if you didn't have those dimples, it would get stuck into laminar flow. You put those dimples in, and you grab the drag graph and you move it to the left to lower speeds, and then the cylinder, the golf ball in this case, drops into this area where the resistance is very low. That's where VIV, though, gets suppressed. So I have to do something different, and we have overcome that by using turbulence stimulation. The numbers that I have here are scales, and I'll talk about scales a little bit later. Now, this is VIV in my lab. This cylinder has turbulence stimulation, has like fish scales on it in a specific location. And this is VIV, then there's transition, then there's galloping. I need to put some sound here. And I'm increasing the speed slowly because we're talking about 8,000 gallons of water. I don't want to break anything, which I have done a few times. So in a few seconds, you will see how it goes from VIV to galloping. Again, just the flow from left to right drives this. Nothing else drives it. So what happens is basically hydrokinetic energy, horizontal hydrokinetic energy, gets converted to mechanical energy, which then we can convert to electrical. That's galloping. And it hits the stops. We don't know where it would stop. It's just the limitations of my lab. We did this about 3 summers ago when I had no idea what I was doing. And of course, we broke through the stops and we cracked the plexiglass. And now we're doing a little bit better. We're smart enough. The third stage is going to the river. And that's actually scale 3. You remember I had 4 scales. This is scale 3. The lab is scale 2. And these cylinders are pretty big. They're like 25 centimeters in diameter. That's 10 inches. And 2.7 meters long. That's 105, 106 inches. This is smooth, totally smooth cylinder. And the speed is 1.9 knots. And you can see that it starts right away. And pretty soon it's going to hit the stops. And that's where we stop the test. Then, those stops were set at 1.5 diameters. In other words, the total stroke was 3 diameters. With the cylinder in my channel, the stops were set at 3 diameters. So the total stroke in galloping was 6 diameters. This is with turbulence stimulation. And I will talk about turbulence stimulation again later. This strip and one on the other side are the turbulence stimulation. They're thin, like fish scales. They're inside the boundary layer. And there it hits the stops, and of course we had to stop the testing. And we went to a smaller cylinder, like a 15 centimeter, 6-inch diameter cylinder, same length, because we want to see how far we can go. And you can see we're hitting the stops again. And this time the stops are at 3.25 diameters. Total stroke, 6.5 diameters. Amazing mechanical energy. Here it's 2 cylinders. And here's when we went to the river. This is the St. Clair River, the Blue Water Bridge. And then we had Dunn Paper company which supported us. They gave us access to the river through their dock, and we're very thankful for that. We got a barge, we deployed it. This is what you've seen before. Now probably you have a better understanding of what you were looking at. The flow is coming again towards us. There is turbulence stimulation on the other side of the cylinder. You cannot see it. And the flow, which was quite interesting, is not uniform anymore. In my channel, of course, I generate very smooth flow and very, very uniform flow. Here there was a change in velocity from left to right of about 15%. Within those 2.7 meters, there was a 15% variation of the velocity, and it still kept going. It didn't stop until we broke a few things. So let me talk a little bit about research and what we have achieved in order to get here, and what is the vision. I've shown you some marine hydrokinetic energy converters at the beginning. There was a point absorber, a line absorber, a surface absorber, and an area absorber. Our vision is to have a 3-dimensional absorber to be able to distribute cylinders in the ocean environment like fish go in a school. And what I will show you also, what I will talk about in a few minutes, is that the cylinders really interact between themselves. I haven't pointed it out when we looked at the 4 cylinders oscillating, but you've probably noticed that the last cylinder is moving with the same amplitude as the first one. You would expect, and this is the case, that as we're taking energy out of the flow, the last one has less hydrokinetic energy to harness, and therefore will have a less vigorous motion. Nevertheless, they all move synergetically, just like fish do in schools. And if you remove one, the first one gets affected. So there's lots of secrets in that we don't know yet. I mean, fish are far too smart for us when it comes to moving in the ocean environment. Well, we operate in 4 scales because there are many different applications that we can talk about if we have time. We definitely want to have an environmentally compatible technology. I don't think that in the next 3-4 decades anything will survive unless it's environmentally compatible. But of course, the driving force is cost. We have to make sure that we generate electricity at a competitive cost. Let me talk a little bit about some technical stuff, but I think that I'll be able to simplify it so that you understand what I'm talking about. And those of you that have background in physics, I think will appreciate this as well. This is like a schematic of the channel we have, and we have those oscillators. And what I have shown you in pictures is this kind of oscillator. You have just a cylinder in a steady flow, supported by these struts and suspended by these springs. And the flow comes in this way and pushes it transversely. Even though these are very benign oscillations, only about a cycle a second, and therefore good for the environment, there are 32 million seconds in a year. No springs are going to last that long. So we need to do something else. And what we did is we introduced controllers. So you have a motor here, which returns, and a controller which returns a feedback signal, simulating a spring and a damper. So instead of having the springs here and the dampers that harness the energy, we put this in a controller in a computer. Now, calibrating for the spring is very simple. You just take the motor, you hang a weight, and you find exactly how much the motor turns. Very simple process. It takes less than a day. Calibrating for damping is very difficult. Damping is nothing like what we teach to our students, that it's linear, viscous, like this. That after we did the system identification over a period of about 1.5 years, we found that there were 4 terms that were nonlinear, static, and then another 4 that were dynamic with memory. Very complex viscous damping. Okay. But after we completed this process, the system identification, my student who was working on that in 5 days collected all the data he needed and finished his PhD. Now, so what we do now is we type in a stiffness, we type in the damping that we want, and we carry out the experiments. You can imagine when I had real dampers and real springs, and I wanted to change the experiment, I had to order springs that were coming from all over the world, the United States, all the way to Poland. We had to calibrate them because manufacturers were not really very accurate in their predictions. And then we had to align for a day or two just to carry out experiments for about 3 or 4 days. So this way, we have a system, which is a virtual system, and it provides feedback. Of course, we have to plug it in the wall. Okay? So that's why I have the first video that tells you that we are actually getting energy. The rest, you can follow it, and you can see something coming out of the wall, and then you wouldn't trust it. But the next step was, to integrate it with a power takeoff system. So this generator, this motor here, also works as a generator. And whenever the system needs a drive, we drive. Whenever it needs, whenever it has excess energy, it produces energy. And of course, springs, whether they are physical or they are electrical springs, they are conservative, so whatever energy comes in goes out. Okay? So that was an important development. Now, the other one, of course, was convert hydrokinetic energy to mechanical. Okay? So increase that. And this is the turbulence stimulation I'm going to talk about. This is just sandpaper. We use this technology a lot in naval architecture and marine engineering when we try to do model testing, and we use small models, of course. We have to trigger the flow to become turbulent in order to match conditions that we have in the ocean. So I used practically the opposite concepts in order to get the cylinders excited more. And this gives you an idea of what the turbulence stimulation does. The first cylinder, remember the smooth cylinder that I've shown you, the smooth blue cylinders that I've shown you at the beginning? Well, I mentioned that when we go from laminar turbulent flow, it shuts down VIV, and that's exactly what happens here, this transition from laminar to turbulent. Then we put turbulence stimulation, just, again, sandpaper in the right place, and we hit the stops. We went through laminar flow and through transition into turbulent flow without ever losing VIV. Then we went back 3 months later. We changed as much as we could the prototype. The stops were placed at 1.9 diameters, and again, we kept hitting the stops. Then we went to the little yellow cylinder that I mentioned, and we started hitting the stops at 3.25. So we don't know how far this goes. But the interesting thing here is that I have VIV back-to-back with galloping with no gap between the two. So we start these flow-induced motions here, and we don't know where they end. What that means in practice is that I can design something that's going to start harnessing energy at 1 knot, and I don't have to change anything for that to keep absorbing energy. All right, this is a little bit more about passive turbulence control. And actually, the PhD student who did this, his postdoc in my lab, is right here, Jim. This is the paper in the sandpaper. This is the roughness of the sandpaper. And this is magnified, of course, a double-sided tape. Now, this roughness generates little vorticity that coalesces with the large vortices. But galloping is a little bit of a different phenomenon. I can't get really into the details of that, but it is caused by the asymmetry as much as the roughness. So if you have a circular cylinder in a steady flow, smooth cylinder, it will not go into galloping. It has to be non-symmetric. For example, if you have a square cross-section, it's symmetric, but as it starts moving, the flow changes direction and doesn't see any more a symmetric body. That causes transverse instability, and that's galloping. Now, look at the interesting fact here. We were trying to find out what really causes what. Is it the roughness that causes the large amplitude motions, or is it just the asymmetry that we introduced by putting the sandpaper? So what we did at some point, we removed the sandpaper completely, and we left just the double-sided tape. That's 192 microns. You know how thin tape is. That's less than 1/5 of a millimeter. And we got amplitudes of 3 diameters, strokes of 6. That's about the size of the fish scale. Now, this, let me try to explain this because I have one point to make. Where did we place that turbulence stimulation? That's sandpaper, think of it half-inch wide, and what this angle here indicates is the beginning of the tape, okay? The beginning where we place the tape. And we deciphered this map, which I think is a great publication. We're waiting to come out. And over here, if you place the paper at the beginning, you have weak suppression. Here we have various forms of galloping, and here strong suppression. So in the process of trying to enhance vortex-induced vibrations, we learn more about suppression that we have learned in the past 60, 70 years. Now, this is 180, P180. Those of you that know, it's a very smooth sandpaper. This is a rougher one, P60, and I'll go between the two. Look how close they are. So, and you can see how broad is the range where I can put the sandpaper, just the beginning of the sandpaper. It's 48 degrees wide, and I can get galloping and enhance the motion. So this is a very robust parameter. I can play with it, the flow can change direction, and I still have a lot of enhancement. So that's how fish probably use it. Now, then there's the other issue, whether to enhance vorticial instability. We talked briefly about it. And this is for improving cylinder interaction. In the channel, I have 4 cylinders. In the towing tank and in the river, we have 2 cylinders. And this is the video that you've seen before. Again, the flow goes from left to right. This is at 1.3 knots, 1.3 meters per second. One of the reasons I'm using that number is because wind farms typically are rated for 12 meters per second. That the equivalent in water is 1.3 meters per second. So we're trying to make comparisons between wind farms and Vivace. And we tried, we started really this Christmas of 2009. We put them together. And actually, was one of my Korean students. I told him, you're not going on vacation unless I have the 2 cylinders in there. I want to see what happens, because I knew something like that would happen. So we started working with the 2 cylinders. He did an excellent job and had it really working overnight. And the distance between cylinders is important. These numbers here that I have between first and second cylinders, second and third and fourth, are almost random numbers. And we tested center-to-center distances of 1.5 diameters all the way to 6 diameters. That is gap of half a diameter all the way to 5 diameters. And we cannot stop that. So cylinder spacing is very robust. And so in the development of the Vivace converter, we use mostly turbulence stimulation, which mimics fish scales, and cylinder spacing, which mimics the spacing that fish achieve when they move fast in schools. Okay. This is how fast it goes. Oh, this is an interesting one. Quite often, people ask me the question, what's the efficiency of the system? And of course, I can give you some efficiency numbers. But in renewable energy devices, a propeller, a Vivace, a buoy, a solar panel, they all have very different ways of calculating efficiency. And we need a common denominator to be able to communicate. And again, the Achilles heel of renewable technology is power density. That is, if we give you some space, put whatever devices you want in there, how much energy do you give us? So in the numerator, you have the power that you harness. In the denominator, you have the volume that you occupy. If you look at fossil fuels, for example, like a diesel engine, we're talking about 25,000 watts per cubic meter. If you look at my first Vivace, we're talking about 51. That was the yellow one at the beginning. Then we went up. This number actually is before we introduced multiple cylinders. And we assumed large spacing between cylinders. And we got this number. You understand that once we do more testing in order to be able to get the numbers for multiple cylinders, we're going to have even much higher, actually, power density. If you scale that to 6 knots, which is still a realistic number, you are within an order of magnitude from diesel engines. So very promising for marine renewable energy technologies. This puts things a little bit into perspective. We made some comparison with wind farms. The 2 biggest wind farms in the world are in the state of Texas. And we compared equivalent, that is 12 meters per second for a wind farm and 1.3 meters per second for water. And the ratio is about 15,000. That's how much energy we have in water. And the good thing, of course, about water is it's the best natural medium for storage. You know that batteries cannot really provide a lot of storage, but the ocean can, water can, and it's everywhere. And these are 3 wave energy devices, Pelamis, Power Buoy, and Energitech, the 3 that I've shown you before. And these are turbine types. Of course, the advantage that Vivace has is that you can distribute Vivace cylinders in 3 dimensions. So you take maximum use, you make maximum use of the space. And the other advantage, of course, is that if you create a lot of turbulence, you can really break it down into smaller components so that the gradient of turbulence change in the flow goes down, which is important from the environmental point of view. In terms of cost, this is a probably complex one. It's the levelized cost, and people in the company did it. I'm not very well educated in economics, or I would say not at all, other than balancing a checkbook. But the cost in cents per kilowatt hour is about 9 to 12. So it's very competitive. Let me say one thing about fishtails, even though we're not doing much now. We worked for about a year, maybe a year and a half on fishtails. You get amazing results. But from the point of view of taking the invention from the lab and putting it in the product, this is complex. In the ocean environment, you want to keep everything very simple. We managed to get very high amplitude motions. But let me explain one more thing about the fishtails, how it works. Ignore this fishtail for a minute. When a vortex grows, you have the 2 vortices generated from the 2 sides of the cylinder. This is positive vorticity, let's say. This is negative vorticity. When one vortex grows big and is ready to shed, it's so strong that it sucks in both its own feeding layer and the feeding layer from the other side. Of course, when this happens, you have negative vorticity canceling positive vorticity. By the time this large vortex sheds, it has 60% cancellation. So the circulation left in these vortices is only 40% of the original one. Circulation is proportional to force according to the Kuta-Yukovsky theorem. So if I lose 60% of the circulation, I lose 60% of the lift. Fish, they're smart. They kick the vortex away before there's cancellation. So I was hoping that by putting this tail in, I will keep the vortices separated longer and let them grow more. And in fact, this works. But the tails are very specialized. Thickness, length, stiffness, size, they all matter. So fish know how to do that. It will take us several decades probably to figure it out. Okay? And the next thing is how to improve our lab. Actually, in December, I took the lab down, and we're rebuilding it now. Slow process, having to get through some red tape. And we're going to improve visualization. I want to show you, before closing, some computational fluid dynamics. The cylinder, as simple as it looks, it's the most complex shape for doing computational fluid dynamics because of vorticity, because of oscillation of the separation point, and so on and so forth. So if you use the entire, literally, computer power of the Department of Defense, you can run about a couple of cycles of flow past a stationary circular cylinder, solving the governing equations. But it takes thousands and thousands of processors. It has been done 3-4 years ago. And if you use more reasonable methods that all of us have access to, then you can get relatively good numbers, up to Reynolds number of about 1,000. You can push it a little bit more. When you go to VIV, just because of the motion of the body, it triggers those heuristic tricks that they put in computational fluid dynamics algorithms and software to trigger the flow. And you can make it in VIV work pretty well up to Reynolds number of about 10,000. Of course, we work in hundreds of thousands and millions of Reynolds numbers. So what we did, and I would never consider that something that we can actually use, but, and this is a lucky break only, nothing to brag about, when we introduced the turbulence stimulation in the mathematical modeling, in the numerical modeling, we got this, which is amazingly close to what we're getting experimentally. So now we can study, just for this range, I don't know how far this is going to work, we can study phenomena that we cannot study easily in the Hydro lab, like what happens in the boundary layer, how does boundary layer in one cylinder interfere with the wake of the other cylinder, how flow transitions from VIV to galloping, and lots of other phenomena. Okay? But again, it's not 100% scientific. Thank you very much for your attention.
Saturday Morning Physics is sponsored by the M. Lois Tiffany Endowment, the Hideko Tomazawa Endowment, the Physics Department, and by gifts from friends of the program.